Professor JWang. Professor Wang is affiliated with the National Laboratory for Parallel and Distributed Processing. He is also a professor at the National University of Defense Technology in China. And he got his PhD, actually all his degrees, in computer science from the same university, National University of Defense Technology. And he's also the director of a very important laboratory. It's sponsored by the Chinese government. So Professor Wang is received a very prestigious award. He is a distinguished young scholar, distinguished research scholar. He's also chair professor, sponsored by a foundation in China. And his research interests include formal analysis and verification of software systems and distributed parallel computing. Professor Wang also served on the editorial board of a few journals, including Journal of Systems and Software. He's also on the steering committee of a few international conferences. So let's welcome our invited speaker, Professor JWang.
Thank you, Chair. Good afternoon. And I'm happy here I'm happy to be here to give a talk, formal verification and modeling verification and refinement of long-running transactions, and to share our experience to find formal foundations for ART. And this is joint work with Zhengbang Chen and Zhiming Liu. And this is the agenda of my talk, and I would like to share with you our results on long-running transactions in terms of process algebra languages. We call it composition CSP and extensions. And the long-running transaction is actually originated from the database area, and it's also called long-lived transactions. And in database, a long-running transaction usually refers to an operation process that needs to be atomic and consistent, and often contains many small atomic transactions, and each of these transactions satisfies the ACID properties. And long-running transaction is the model of ART, long-running transaction is SAGAS, and as we know that it was proposed in 1987 in Sigmund conference, and the key ideas of ART model is a composition. And composition is actually a common used concept in our daily life. If one has done something that cannot be rolled back, and he can do something for composition. And here is a car accident example that the non-responsibility side will be compensated by the responsible side or an insurance company for the damage of the car. And actually, such case and the similar situations appears in computing too. And sometimes it's not, however, sometimes it's not easy or even possible to recover the system state to exactly the original one. So let's see the examples in database. If you need to process, say, 10 million user accounts, and the computing process probably needs a long period, say several days or even longer time. And during this process, so one cannot isolate the related resources, otherwise the system will not be acceptable. So in database, in a long-running transaction, therefore in activities that will have its composition activities. And if a failure happens in a long-running transaction, the composition activities will be executed and to compensate the effects of the before successfully committed activities. So let's see, for the activity A1, and we may have its composable part B1, and if A1 executed successfully, we will record B1, and for A2, we will record its composable part B2, and A3, and the corresponding part is B3. And if there is a failure, in case of failure, an error, then we will recover the original state of the system to execute it B3, B2, and B1 in a reverse order. And this is exactly the Sega's model of compensation. So by using this method, we can get satisfiable acceptive activity and consistency. Okay, so what we consider in our context is distributed computing. So as we know that nowadays a distributed system consists of components and services provided by the worldwide distributed organizations. And these components or services will coordinate to accomplish a task. And such a coordination happens in a highly dynamic environment. So in this case, how to ensure the consistency in case of failure is quite important. And actually, in general, one cannot isolate the resources of different organizations. For example, when an agency books a trip for its customer, while the agency books the flight, it cannot isolate the database of an airline company. So what we can do, fortunately, we can have the long-running transactions. And the long-running transaction, that is to say that the travel agency it's not necessary for the agency to isolate the resources of the airline company, and it can refund the ticket if a failure happens. And as we know that in the industrial community that for the languages such as WSBPL, and it has provided the composition-based fault handling, and also the flexible recovery mechanism for ARTS. So we can program in ARTs in WSBPL, and this is a specification document of WSBPL 2.0, and we may find that for each scope, BPL scope, we can have a fault handler and a composition handler. Once in case of there is a fault, and the fault handler can use the composition handler to recover the state of the system. So we can ensure acceptive the consistency of composable web services. Okay, so the industry community goes ahead, and how about its formal foundations? And during the past years, we have some formal languages for long-running transactions. For example, the CCSP, which will be investigating this talk, and the structure, activities, compensation, and Sega's calculator, and etc. And using these formal languages, we can model of the long-running transaction to provide a rigorous semantic foundation. And Also, we can provide formal semantics for the industry languages such as BPL. And also, if you want to build some tools to verify the property, the correctness of the BPL programs or ART, and it will play a solid basis for the verification. So what we are considering is we try to provide a formal foundations for long-running transactions to ensure the correctness of ARTs and to improve the reliability of ART design. But the story is not so simple. So basically in this talk we would like to investigate the approach, process algebra language approach. And what we started is a compensating CSP. It's actually proposed by Michael Butler, Tony Hill, and Carla Ferreira. And first I would like to use the CCSP to introduce the background of our research. And we may find that there is some inadequacy to give the foundation of the ARTS, especially the non-determinisms, deadlock, and leave lock, and there is no idea of the refinement between two CCSP processes. So we would like to have extend the CCSP and to include all the concurrent features which is necessary to modeling and reasoning about the ARTS. So we start from the CCSP. CCSP is a process algebra language based on the CSP. And for each process, we have some basic operators of the process. So in CCSP, there are two types of processes. One is the standard process, which is actually similar or the same in the original CSP. What is interesting that to modeling ART, we need composable processes to model the non-learning transactions. And in the original CCSP, Professor Butler and Tony Hoare, they define a semantics called terminated trace semantics for CCSP. So, okay, so this is the syntax of CCSP, and we may notice that the P is a standard process. It's actually the same as the original CSP, except the structure, the transaction block. And this is PP is actually the composable process. And for this, it will be used to modeling the ART, and with the transition block, you will to bridge the connections between the standard process and the composable process. And also there is a special process flow and yield. And we can also see that the PP, what is the new in CCSP, it is actually the composable process. And the basic form of the PP is P divided P. And these two P are the standard process. And we may know that P is the first P. The first P is actually a forward process, which will be executed, and the second P is the composable part. So it's actually a composition pair. And if P executed terminates successfully, then we'll record the second P, say Q, to record it. And if there is a failure happens in the future, and we will execute the second process P, say P, to recover the state of the original state of the process. So let's see an example. And here is an example. And A1 divided B1, and the semicolon is the sequential composition, and A2 divided B2, and semicolon composition with row. Okay, let's see. So first, that we will execute A1, and it, of course, it terminates successfully, and we will record its composition part V1, and then we will sequentially compose the A2, activate A2, and record B2 here. And if there is the exception, and then we will compensate the previous successfully committed activities. First, we will execute B2, and then B1. So that's the intuitive meaning of the expression. Okay, so let's consider the semantics of CCSP. Original CCSP is called terminated trace semantics. The ideas of the terminated trace semantics is actually that we use the set of the terminate trace of a process to denote the semantics of the process. So that's a basic idea. So for the T, A, we can see that there only is one trace that the A check mark, because means that it will execute it A, and then we terminate successfully. And that is actually that we have in CCSP, a process can terminate in 3 cases. The first case is it terminates successfully. That is marked by the check mark. For example, the T skip, that is a check mark. It terminates successfully. And the second case is it can terminate exceptionally. It leads to exception, such as a T through, that this process is actually, it contains only one trace and exclamation mark here. And the third case is that we can, it actually means, it's a question mark, there's a question mark here, and it is a yield interrupt. So this one is yield interrupt. It can be used in parallel composition later to model that the exception happened in one process, and this process will interrupt other process. So the yield, the traces could be 2 cases. The first is terminate successfully, or it will be interrupted by another, the process in parallel with it. So this 3 kind of terminates. So, and for the sequential composition and the parallel composition and the exception handling is quite similar to the original one, CSP. I would like to give the details of the expression. Let's see some of the examples. And okay, let's see these 2 ones. And A through parallel with B. And in this case, we may find that using interleaved traces, we can say that first you can execute A, and then B interleaved with B, and there is through that except handling, and this is one of the trace. And we can also execute B first, and there is A, and ended with the exclamation mark to indicate that there is exception. Okay, so, and we can see this expression, A through parallel with a yield B, and in this case, in these expressions, we can have the 3 cases. And the first case is that it means that the yield and the through, that is an interrupt. So we just executed A, and the process will ended with exclamation mark. And we can also use the yield. It could be where the terminates successfully. So we can have the other 2 cases. The one is the B, we execute B, and the A, and ended with exclamation mark, and the A and with B, and ended with exclamation mark. So that's it. Okay, so now we can turn to the composition, the semantics, the terminated trace semantics for the composable process. And we can say that that is a composition pair, and P divide Q, and we know that B is a forward process and the Q is a composable process. So its terminate traces is actually we use S1 divided S2 to express it. And S1 belongs to the terminate trace semantics of P, and S2 belongs to the terminate trace semantics of Q. So what's the meaning of this, the operator, the divide operator between two traces? We can see there's two cases. The first case is S1 equal to T concat the check mark. So in this case, it means that the forward trace, the forward process terminates successfully. And in this case, we must attach the composable, the trace. So we have the composable pair that S1 is a forward, the trace of the forward process, and S2 is a trace of the composable process. And otherwise, it means that S1P does not terminate successfully, so it's not necessary to attach the second part, the composable part, to the semantics. So we just leave the S1 here and use the check mark here. So actually, the behavior of Q will be ignored. So it's not necessary to compensate the effects of the forward process. Okay, let's see the example. And for A divide B, and we can see that A, of course, A will be executed and terminated successfully. So the second pair of the composition pair, the trace is a B check mark. So it's okay. So for this example, that we can see that A semicolon a sequential composed through divide B. We know that the first part, this part will not be executed, will not terminate successfully. It will be ended with the exclamation mark. So in this case, that we just put a exclamation mark here is a terminate trace of the first part, and just attach the checkmate, the check mark here. Okay, so how about the composed operators between the composable processes? I would like to just to list one example, that's a sequential composition, and which is quite important. We can use this to formalize the Sagas model. That means we have an example in the previous slides. We can say that PP and QQ, and these are two composable processes, and we would like to sequential compose it. And it's actually that there is a semicolon is composed of two composable pairs. And the P and the P prime belongs to TP, and the Q prime belongs to TQ. And we would like to notice with the formulas in the box, the meaning is easier. It means that if the forward, if the first process, okay, if the forward, if the first process, the forward process of the first process terminates successfully, what this means, and then we should record the P prime, and consequently Q prime, and the composable pairs. What we noted that the composable activities will be executed in composite to the order of the original forward process. So in this composable pair, we may notice that the original execution of the activities is a P semicolon Q, and when do the composition, we will change its corresponding composable activities. That's Q prime semicolon P prime. So that's it. And the second is that if PP cannot be terminated successfully, then we just the semicolon which has deposed the second one. And here is the example, and this example means that for A1 divided B1 and A2 divided B2, and we are first executed the A1 and A2, and it terminates successfully, and the composition activities were exactly the B2 and the B1 in the opposite order of the previous one. Okay, so then we may consider that the meaning of the transition block, the transaction block. The transition block actually it can transform the composable process to the standard process. So it's two cases. We have two cases. The first is that it defined, the first case is said that S1, the first part, the S1 actually does, there is exception that at the end of the S1, so it will, the forward process will be compensated with S2. So we just concat these two traces, S1 concat S2. That's it. And if the first one it has been terminated successfully, so it's not necessary for us to compensate the activities. So we just use the S1 and concat the check mark. Okay, so the examples we can see, we just compare the last line, the examples in the last line. So the A divided B semicolons rule. And we may notice that the semantics, the terminating semantics is the A exclamation mark and with B check mark. That's it. And with the block, we can say that we should, then we transform it to the standard process, and we should to execute it in the composition part. So the box of the square of the transition block of A divided B and through W, there will be we executed A and we execute its composition part and terminate successfully. Okay, so with the previous semantics, we can see that the Sega model was typically like this. We can execute A1 and record B1, and execute A2, record B2, and when there is exception, and we will compensate to execute B2 for composition of A2 and B1, then B1 to compensate the A1. So the treatment semantics is exactly the A1, A2, B1, B2, B1, and terminate successfully. Okay, that's the background of the CCSP, and when we consider to examine the expressiveness of the CCSP, we may find that we need extending it. First of all, the concurrent systems, if we consider its expressiveness, it can have the ability to model non-determinism. And also it can model the deadlock and also the left lock. So, however, in CCSP, none of these features has been supported in the original one. So the reason is basically because of its lack of some syntax, also lack of the ability of the trace semantics. And with the CCSP, there's no definition of refinement. So one cannot design the ARTs by refinement strategies. So what we want to do is we would like to extend the CCSP and to deal with, to enrich its ability to express non-determinism, deadlock, as well as live lock. And also we would like to find a natural refinement order between over its semantic domain. So the first step is the non-determinism and the deadlock. What we will do is first we would like to extend the syntax of CCSP. So we notice in CCSP it does not distinguish the internal choice and external choice. So we will extend the CCSP with internal choice and extended choice. We also extended with synchronization and with hiding and renaming. And also we have a unique processor stop to model it's actually a syntax sugar for the deadlock. Okay, so just as the semantic evolutions in the development of CSP and from the trace semantics to stable failure semantics, we also consider that use the stable failure semantics for the extended CCSP. So the basic ideas of the failure-based semantics is that we try to use a failure to give the semantics of a process, and a failure is actually a pair. That the first is the trace. S is a trace that can process. It describes that a process can execute it. That the trace is prefixed closed. We will see later. And the X is actually the refusers. That the set of the events that a process refuses to perform after executing S. So let's see an example. We have a process expressions A semicolon B, and at the beginning we can see that the trace is actually the empty trace, and the refusers is actually the refuse to execute any events except A. And after executing A, we may notice that refuse to execute any events except B. So we can see that the trace is A, and X is a refusal event, and if the B does not belong to X. And after that, there's refuse to execute any events except the check mark. So it will terminate successfully. And after check mark, we can see that refuse to execute any events finally. So that's the idea of the failure-based semantics. Okay. So what's a deadlock in this semantics? A process deadlocks if it refuses to perform any events after executing a non-terminate trace. Okay. So the rest of the work is we try to give the semantics for the extended CCSP. And the standard processes, so we can just define the semantics quite similar to the stable failure semantics for CSP. And for the standard process, its semantics is actually a pair. That's a trace set function, TSP, and a failure set function of FSP. And for the composable process, so there is we should notice that it is a triple. So for the composable process, its semantics is a triple. The first one is the first two, T and F, is actually gives the semantics of the forward process. So that's it. And C is actually the composition part. For this composition part, we also call it the composition set function. The CPP is actually also a triple. And for this triple, that S is actually a terminate trace, terminate successfully trace. This one is S. And TF, these two describes the composition, the composition process or composition activities process of the second one. So that's what's new, that the stable failure semantics in CSP, in the extended CSP. Okay, so we just see some examples. For stop, we can see that the TS stop is it's actually a standard process, and it's the trace set is empty set, right? Okay, for its refusers, it's X. For the empty set, we can say that X is all the alphabets and include all the terminate mark. So it's actually that means that the stop, the trace of stop is actually the empty set and empty trace, and it will refuse any of the events at the beginning. Okay, so for the internal choice and the external choice, with the stable failure semantics, we can differentiate the meaning of it. So the difference is at the beginning. The internal choice will refuse an event if any sub-process can refuse it. And for the external choice, will refuse an event if both of sub-processes can refuse it. So that's the difference of the internal choice and the external choice. Okay, so we can have a to express the ideas of the previous statements that actually for internal choice and internal choice and external choice, the trace set are actually they're the same. They're the same. However, the second part is different, and we can see for the internal choice we just to simply the union of these two sets, FSP and FSQ. However, for the external choice, we will say that the refuser set, the events, will be exactly the FSP and the intersection with FSQ. So that's the difference. Okay, here's some the example, and I skip it. And for the synchronizations of the standard process, we may notice that the parallel composition with synchronization on X can refuse an event out of X if both sub-processes can refuse it. And the parallel composition with synchronization on X can refuse an event in X if any sub-processes can refuse it. So with these semantics, we may consider the modeling of the deadlock. Okay, the deadlock is, of course, we will model the deadlock with a synchronization. So actually, it's a no synchronization, no deadlock. So let's see this example. The A parallel with B, and the X is A and B. So for FSA, is actually we notice that actually that what we will consider is the first part is at the beginning of this one that is empty trace, and X is A does not belong to X. And for B is actually the empty set, and X is B does not belong to X. So what we will derive that Fs and A parallels with B over the AB is actually, we can see that the empty trace, and the X is actually all the events, include A and B, and question mark, check mark, and exclamation mark. So exactly the stop, Fs stop. Okay, so let's turn to the composition part. P and the divided P. Okay, let's see the examples. First is actually that P divide P and A divide B, and for in this case it's also the pair. We notice that the first part, actually the first part is the T and F are the semantics, are the stable failure semantics of the forwarded process, that TSA and FSA, right? Okay, so what's the third part? The third component is actually that for the successful terminates trace A checkmate, and we will record the stable failure semantics of the composition process. So it's actually the B, so TSB and FSB. That's it. Okay, so for this process, there is internal choice. We can see the internal choice A and A through divide B, and in this case, what we can see the third element, and there's two cases. The first is we execute A at a terminates successfully, and in this case we can see we must record the behavior of B, right? Okay, so the second case is this one, that A exclamation mark. It means that this one will not terminate successfully. In this this moment, it is not necessary for us to associate the corresponding composition activities. So we just use skip here. That's okay. Okay, that's the similar strategies. We can define the internal choice and the external choice of the composable processes. And here's the example. Okay, we can see that for this example, there's two cases. The internal choices we executed A1 and record B1, and there is exception. Then we will execute B1 to compensate the effects of A1. And since it is internal choice, we can execute it A2 and record B2. And when there is exception, and we will execute B2 to compensate A2. So this formula, this expression of composable processes actually is standard composition. Yeah, standard process. Okay, so similar to the case in the terminate trace semantics, we can define the sequential composition PP and QQ. Okay, so sequential composition of composable processes, and what we would like to do that first we are sequential composed of the forward process of these two process, right? And PPF and QQ semicolon PPF, QQF and PPF and QQF. And this means that the forward process part of PP, of composable process PP. And what is interesting that we will consider C. The C is that if STF, and there's also the two cases. The first case is that we may notice that S1 is T concat check mark, and it means that the first part will terminate successfully. And in this case, we should, if we will do the composition, that the composition part is we should do the QQC and PPC. We just execute it in reverse order. And the second case is that the first forward process does not terminate successfully. Then it's not necessary for us to composable to do the composition. So the idea is the same. However, the formula becomes more complex. And we have seen the examples of this one. This example is very important and has appeared in my slides several times because it's actually to reflect the ideas, the constraints by the Segas model. So it means that we can, our semantics can reflect the Segas model nicely. Okay. And for the parallel composition, and we notice that for PP and QQ parallel over the X, and we can see that the idea is that for the forward traces, the forward process, we just do the parallel composition of these two. And for the successful terminate traces, we will make its composition part to execute it parallelly. So it's the same. Okay, let's see the example. And for this one, we can see that these two were parallel. And in this case, we can see we will execute these two. However, it's a deadlock, right? So the semantics is exactly the stop. And for the second example, we can see that A divide B1 and A divide B2. And in this case, they were synchronized. And if there is exception happens, we will have first, we have two choices. So first, you can compose, you can execute B2 and then B1, or you can execute B1 first and the B2. So far that we have some extension to the CCSP, and it can model the non-determinism, and it also we can model the deadlock with a synchronized parallel composition. So it is actually a new semantic model for the extended CCSP. However, at the moment we still have some features that the first is a live lock, so we don't have the recursion in our expression. So no recursion, no left lock. And also we don't define natural refinement relations over the semantic domain. So just as the development of original CSP, now we should consider the finite a new semantics. First, we extended the syntax of the CCSP, and because there is no recursion, so we would like to extend it with some recursion facilities, and also we would like to define the refinement with respect to the stable failure model. However, what we want to say that it is quite hard to define over the stable failure models. Okay, so this is the extended CCSP, and in this we may notice that we have now we have a recursion facility in the standard process and also the composable process, and we also have the speculative choice here, which is very popular in the programming of web services over internet. Okay, so just as a development of CSP, we will develop the failure divergence semantics for the extended CCSP. And this semantics, we look forward to supporting the recursion interpretation, and they use recursion to model the live locks, and we can also have a nature refinement definitions. So what is failure? What is failure divergence semantics? And the failure, this one is defined as before. The S is the process can execute, the trace that process can execute, and the X is a set of events that the process refuses to perform after executing S. So the divergence is actually a trace of S, and the process enters a chaos state after executing S. So when a process enters chaos, it is totally unpracticable, and it can perform and refuse any event. And we use dive to denote the process can divergence immediately. And we can also have the properties of the divergence. The first divergence is suffix closed, and the divergent process can refuse any events. And a terminated divergence must be generated by the non-terminated divergence. This is actually something like the actions of the divergence, and these constraints were satisfied by our semantic domain. Okay, for the standard process, it's quite similar, just as the terminate trace semantics and stable failure semantics. The standard process, the semantics of standard process is actually does not change for much, and it's actually that as FD for the standard process, we defined its failure set function and also the divergence set function here. And here's an example. We can see DA, the divergence is actually the empty set. So it never diverges. And the DD contains the empty trace. It means that, so with the function, with the actions, we have showed that in the previous slides that DDF contains any traces, actually the divergence at the beginning. So for the refinement of standard process is actually we say that P2 refine P1 means the refining process will have more or less divergent or failures compared with the refined one. So it is more deterministic. So this is a very nature, the refined order over the semantic domain. And for the live lock, we can see that it is quite easy. So with the recursion, we can see that mu P A semicolon P is actually executed A infinitely. So the mu P and the A semicolon P, we're hiding the symbol A, and it's equal to the die. So we get it. So what is interesting that how to define the failure divergence model, the semantics for the composable processes. So how to define it? That a little bit difficult, but the idea is simple, but some technical details is not so easy. The first is we based an existing one, just as the way we have used in the stable failure semantics. And the second is we should build a new model, and in this model we try to find it out. See? Well, okay, here. So let me to explain. Therefore, the composition for the composable process, the PP is actually the TFC, right? And the trace set, failure, and the composition part. And for this one is actually for the successfully terminate trace S, and we have the TF for the semantics of the composable activity. So we would like to extend this idea that the first part is forward processes, the semantics will be captured by FD, the first two elements, and for C, we see that we are for successfully terminated trace, we associate this FD semantics for the composition activity. That's it. So can we extend it the way the semantics in this way? However, we failed to find the complete lattice or CPU over this domain, and we cannot define a nature refinement order. So we have to consider the second approach. The second approach is for the composition process is we should find the semantic model and make the algebraic laws of the intuitive of our recognition of composable process. Okay, and the refinement, we also need to provide a fixed point theory for the recursion part of our language, and also we have a refinement order. So I have to accelerate. So the idea is we change it. First, FD is actually the FD semantics. These two is FD semantics of the forward process. And FC and DS, we notice that for the terminate trace of the S, and the S prime and X is actually the failure after the executing of successful terminated trace S, and the S and S prime for this terminated trace of S and S prime is actually the divergence trace. So that's it. We split it, so it becomes a four tuple. And with this semantic model, we can have a very nature refinement order. That is this one refined. This one is actually it is more deterministic. That's it. So it seems easy to understand, and the domain is the CPO, and the order is nature for refinement. Okay, so we can get the semantics model of this like this. This is a forward failure set of the forward process, and this is a forward divergence set of the forward process, and this two is for the composition part of the failure. Okay, the semantics is we can define, we can have so let me have this one, as we can see that A divide B, and it's FA, right? FA, and there's no divergence set, it's empty set. And for this terminate successful terminate trace A checkmate, and we associate, right? We associate FB here, and there's no divergence set. So that's it. So it seems when you know the answer, it seems easier. And we also define the operators are continuous. So we can use the least fixed point semantics for the recursion, right? And div is actually the bottom element of the expression. Okay, so for this one, we can say that we first execute A. It's actually non-deterministic. It is non-terminated. Okay, so executed A, not terminated. And this is actually that of this one. And for the speculative choice, we can say that we can execute it that A and A2 throw in parallel. It's actually the speculative choice. And each of the branch successful, and it's okay to me. So we can, in this case, that of course this one will be throw as exception handling, so the B2 will be executed, right? And when this exception comes, and we will execute B1. So it's actually equals to the expression of the standard process like this. And we can also have this one similar, and A1 and A2 in parallel, and we can execute it. We can just the speculative choice can choose either of this one to compensate, and this one choose A1, and when there's an exception, we will execute the B2 for the compensation. And we can also choose B2 first, and when the exception comes, we can have the B1 for the compensation. Okay. Okay, so I'm afraid I have to skip the slides. And okay, so far now we can have all the features, essential features of a concurrent systems, say the non-deterministic, deadlock, and the level lock. We defined failure divergence semantics for the extended CSP, and we defined the refined order over the semantic domain, which is actually that depends on the non-determinism of different processes. Also, with the semantics we provide, we can have some algebra laws, and these algebra laws of standard process, and is quite compatible to our intuitive meaning of the recognition of the non-learning transactions. And for example, we can see for the refinement that the internet choice is actually we can P refinement to the internet choice and P and Q, and also we can have some the units and zeros for the exception handling, and the exception handling is actually distributed over the internet choice, and the exception handling is also enjoys association laws. Okay, so for the parallel. Okay, we can also have the algebraic laws for the composable processes. We have the units and zeros, and this is quite interesting that the distribution, the transition block over the internet is actually distributive over the internet choice. Okay, and for the refinement laws, we can say that that is interesting that we have a nicely connection between the refinement between the composable process and its corresponding standard process. So if P1, if PP2 refinement PP1, then we can say that its corresponding transition block, the standard process refinement to the corresponding one. Okay, we can also reduce the refinement between the composable process to the one in standard process. So we have with these laws we have bridged the gap of the standard process and the composable process. And this diagram means that the Sega models works well in our semantics model. Okay, we can also have use the YEL to provide the developer, the designer, to to specify the places which the long-running transaction can be interrupted, the exact places, and it's actually non-deterministic facilities to include the different choice of design decisions. Okay. Okay, so let me conclude the talk that first, I think we would like to share that our experience to give a semantic theory for the long-running transactions, and they support the modeling and reading about non-determinate deadlock and the live lock, and also we have a nice refinement order over this semantic domain, and we can get a nice algebraic laws for reasoning about long-running transactions. And at the moment, we are working with colleagues at the National University of Singapore to build a path-based model checker for the extended CCSP, and we would like to also to try to build to give the semantic series for the industry languages such as BPMN. Okay, that's it. Thank you very much.
We have time for a couple of questions.
Can you give us a real example that can show how we take advantage of this, new model, new method, whatever?
Oh, yes. I did not mention the case studies in this talk. We have 49 pages around articles in selected computer science. And in this journal, we have the example, for travel agency example, to see that we can use the algebra laws to reasoning about the properties what we concerned for the long-running transaction. So, and the paper has been published online now.
Do you have more questions? Please use the microphone there.
So you said some the extended CCSP are related to some web service programming. So can you give an example show how it can be used in such a popular issue?
It's actually that we can, for example, use actually what I gave the semantics for the talk is it is not intended to be used directly in verification. So actually, we would like to build the verification tools based on the semantics of the semantics of CCSP. For example, for the industrial languages, BDSL, BPL, and we can translate it. Actually, the first step we can translate to the expression of CCSP, and then you can use the verification tools of CCSP to check the model. For example, you can check whether the non-linear transaction will have design if it contains a value. And such kind of tools will be a model checker, which are in development in cooperation with So we would like to use the semantics to lay a foundation to increase our confidence of verification tools. But when you in practice, I don't think it's intended to use these semantics to reading about properties by hand. So maybe at the end of this year we can publish and you can find that there is a tools associated with PAT, and there is extension of PAT to model check with CCSP.
So because of the time constraint, we are going